Can everyone see it okay?
We can see your slides and we can hear you very well. So let's just wait a few seconds for people to join, come back, and everything is looking very good. Okay, all right. So welcome back, everybody. We're starting the third session for our third day for the UCF workshop. It is my pleasure to introduce Atom Patel from the University of Waterloo, who kindly agreed to give us an invited talk here at the workshop on the topic of remote OpenMP offloading with Ucx. And this is some work that Atom has kindly worked on and contributed in the community with Johannes Dorfert from Argonne National Laboratory. And we are very happy to hear about his work, and which has a very nice abstractions and implications for how we can program remote devices in the area of like DPUs or other systems that are remote. So I'm going to be using this opportunity to introduce their work here to this community, and I'm going to let Atom introduce himself to say a little bit more about himself, and he can start his talk as well. Thank you, Atom, and this is yours.
Hi, thank you, Oscar, for the very, very, very exceedingly kind words of introduction. So like Oscar mentioned, I'm Amin Patel. I'm an undergraduate student at the University of Waterloo. And this is joint work with Johannes Dorfert at Argonne National Lab that I did over 1 or 2 internships with him. The sort of motivation behind our work was that OpenMP remains very widely used for intranode parallelism in HPC. Containers are coming along, but in terms of portability and the level of abstraction that OpenMP can provide, it still remains pretty fairly well used. But a problem that we noticed is that when people want to extend OpenMP applications to distributed systems, it gets exceedingly a bit difficult. It gets a bit hairy. Typically, this involves the addition of a new model, such as MPI, or trying something new altogether, like X10 or Chapel. And there are many large applications for which this is the only way, because the features MPI provides, they're unmatched. But for simple applications, if someone just wants to use remote CPUs or remote GPUs, we felt that there had to be a simpler way. With the introduction of Accelerator Offloading into OpenMP, which is, I think, 4 or 5 years ago, OpenMP has a way to use the exact same pragmas from OpenMP that apply to CPU parallelism to GPU parallelism as well. In the past, because of OpenMP's abstraction layer, it's typically been slower compared to vendor-specific languages such as CUDA. Obviously, because something like CUDA requires you to explicitly manage memory, it has a lot more explicit programmer-controlled handles, so people can tune it better. Recently, however, Johannes Dorfert and I, as well as a bunch of other people at Argonne National Lab, have been working on trying to get the open implementation better, so we can actually get reasonably CUDA-like performance even within OpenMP. All of this matters because we're trying to say that, in general, OpenMP can and should be used in some cases to do distributed programming. So the overall project goals that we have is that we want to allow OpenMP programmers to use remote CPUs and GPUs as if they were local ones, as in we want them to be able to transparently offload. The 2 main goals that we had were that it should be productive for developers, so programmers don't necessarily have to learn new models or change their workflows. If their applications simply require remote GPUs and CPUs, they should be able to do that easily. And obviously that the resulting programs are scalable, as in you don't suffer an enormous penalty hit by not using something like MPI. I do want to make a few disclaimers before I actually get into the meat of this talk. It's that, like, this is not trying to create a competitor to existing distributed programming models. Neither Johannes or I are in any way even remotely close to being experts in the way that UCX is used or can be used or performance regarding it, similarly with MPI or distributed programming, and that we developed this as a proof of concept implementation, and that is what it is still. we're still trying to look for more active use cases where we can try using our work to program useful things. Sort of a basic use case that we kept in mind when developing this was sort of like a distributed merge sort, right? Let's say you have some array, you want to sort it using merge sort. The idea would be that you would keep bisecting the array, and you would offload each section to different devices, and each device would sort it and then return it. This is kind of what it would look like using OpenMP offloading. In this case, merge sort is kind of an iffy example because sorting isn't really an operation that's necessarily much faster on a GPU, but you can imagine any operation that requires a lot of computation and needs to be distributed in a way such as this. So before I really get into what we did, I want to talk a bit more about how target offloading works in LLVM. So what happens is you have the user code, let's say here, it gets compiled using Clang or Flang with a few flags. One of the flags specifies all the architectures that you want to compile it on. I'm going to go over the architectures that we support in a minute. Clang uses these architectures and produces a fat binary. This fat binary contains whatever device code that has been compiled, whatever kernels that need to be executed, as well as some host code to sort of wrap around the kernels that you're executing. The host code typically loads a library called libomtarget, and libomtarget offloads all of the actual work onto device-dependent plugins, and the plugins actually handle working with, let's say, the CUDA driver and the device itself. So this really modular architecture lets OpenMP target offloading support new architectures very quickly. And we also support a lot of the more common ones already, but in case there are new ones, we can support them very quickly. The sort of main idea that we had was instead of having a direct link between libomtarget and the plugin that you're trying to offload onto, the goal would be to let this happen over the network. Currently, OpenMP target offloading supports few architectures. We support AR64, AMD GPU, CUDA, x86, PowerPC, and VE. And all of these have been tested and to varying levels of degree. During our work, we used two backends. The first one that we worked with was gRPC. We started off with it because it was simply easier to use, and it only required commodity-grade hardware, so it was easier to work with. Because we were using gRPC, it comes with a default serialization library that's pretty hard to remove. So we use protocol buffers for serialization, and this backend is publicly available and has been upstreamed into LLVM, and it's available since LLVM 12 under one of the CMake flags. Right now, we're obviously moving on a port towards Ucx because obviously, and we also had to write our own custom serialization for it, and it's in development, and it's pretty close to starting to be upstream, but it's not quite there yet. Just a bit of background on gRPC. gRPC is an RPC framework developed by Google. Because it's meant for sort of more consumer-grade applications, it has support for things like load balancing, tracing, health checking, authentication, things that we at this time are not really thinking about, but those were extra features that gRPC kind of provided out of the box. The sort of major limitations that we had in this implementation was that it uses protocol buffers for serialization, which is really only optimized for small message sizes. And for a lot of the application that we were testing on, there were large matrices being passed back and forth, and protocol buffers, it wasn't lagging, it wasn't slowing down, but you could feel that there was room for improvement. The sort of biggest limitation that we had with it was that it has a large number of dependencies. It ports in a lot of other libraries from Google, and we felt that it was completely unnecessary to have all that in there. Another big problem we had with it was that it doesn't have quite the kind of zero copy semantics that we want. So we were having a lot of unnecessary copies, which obviously we want to avoid. And the biggest one, I think, is that it was limited to TCP because it's meant for non-HTTP situations. We tested this implementation on the Google Cloud, as well as a bit on Theta GPU, which is one of Argonne's GPU clusters. And we got pretty excellent weak scaling results for some of our applications, even on commodity hardware. So I'm going to go through one of those results now. So this is a set of benchmarks that we ran. This is a benchmark that we ran on Google Cloud. These were like individual instances. Each instance had one GPU. The network bandwidth wasn't aggressively high. I think it was 25 Gbps. And here, this is an application called RSBench. RSBench is a proxy app for OpenMC. It contains the biggest computational kernel and sort of strives to be an efficient stand-in. Here, the purple lines, which in this case is here, as well as the other one here, those are the default instances, the default runs for the small problem size and large problem size. The small and large simply refers to the amount of memory that the application will use, how large the simulation is. These other lines here, as in the blue ones and the yellow ones, etc., those are experimentations with the number of iterations that each kernel does, so effectively trying to reduce or increase the computation time it takes to see how the trade-off goes. So here we see that for RS bench, at least in the default case, we see that as we go from one remote node to 4 remote nodes, as in one remote node with one remote GPU, 4 remote nodes with 4 remote GPUs, even in the default case, we get pretty excellent weak scaling in that if you have 4 times the number of GPUs, you're almost 4 times faster, because again, this is weak scaling. For XS Bench, which is another proxy app for OpenMC, we see quite a different result. This application swaps in memory usage for computation time, so it transfers more data and does less compute. So here we see that in the default cases, we get pretty okay scaling, about half as good as RS Bench. And obviously, if you make the computation time even less by factors of 10, you get significantly worse scalings. But if the compute time is long enough in proportion to the data, you see that once again, you can obviously get pretty good scaling. Additionally, by the way, these two are both with gRPC. Now onto the actual Ucx portions. For Ucx, we obviously tested on Theta GPU. Theta GPU is one of Argonne's clusters. We were able to get 16 nodes. Each node had eight A100 GPUs. And they were connected by the networking device that it has. Here we see that even for XS Bench, which was the worst one out of these two, we see that we get pretty excellent scaling for the small case as well as for the large case. We see that when we get to 15 nodes for the small, we get less than a 10x normalized runtime. It's a strong scaling, by the way. And for the large case, we get closer to about 13, 14. But the sort of biggest takeaway here is that although the scaling isn't exceedingly linear in the sense of being flat, but we were able to scale up to over 120 GPUs without any source modifications. The original application for XS Bench and RS Bench uses a single GPU. The only modification we did was to distribute that work over the number of available GPUs, and suddenly we get this pretty great scalability. The largest overhead that we had here wasn't even from our remote offloading implementation. It was strictly from the fact that XS Bench requires a large amount of data to initialize, and this was 120 copies of that data across the network, which is obviously bottlenecked by the host. The sort of limitations that we have right now in our implementation is that because once again, this is prototype implementation, we're using tag matching only. So we're not using RDMA, GPU to GPU copy. These are things that we intend to implement soon, but we haven't quite gotten around to it yet. So in relation to everything else that you've seen at this workshop, we have relatively high network costs. So there's a lot of further tuning that's required. Evaluation is a bit sparse because there's a chicken and egg problem here. OpenMP applications are typically not multi-GPU. As soon as it becomes multi-GPU, people incorporate an MPI, and OpenMP plus MPI applications are surprisingly difficult to dissect. The sort of biggest thing is that if you want to use this effectively, you need to have a sufficiently long compute time, obviously, to rationalize the network costs. And sort of the biggest limitation here we have is that OpenMP's accelerator device model kind of prevents some optimizations that would be nice. So as an example, what I mean by this is that the OpenMP device model considers each GPU to be an independent device. So there's no concept of a hierarchy. So what happens in this case, let's say, that for the 15 nodes with 8 GPUs each, what's going to happen is, assuming that this is true for XS Bench, which it is, but it's not true for any generic application. But for XS Bench, the initialization that goes on the primary host that it offloads onto the GPUs, it's the same per device. So in the case of the 15 nodes, it is going to do 120 copies when it only needs to do 15, because the data is the same per device. So you can copy it once to the host and then copy from the host to the devices individually, rather than doing them all separately. You're sort of limited by the star topology here as well, which is obviously not great if you want to scale much further beyond 120 GPUs. However, in the case of RSBench, when we implemented a symbol optimization, because we knew that for RSBench and NexusBench, that this sort of duplication exists, we see that even for the RSBench small case, where we didn't even see that much of an overhead, we see a much better scaling result, where if we scale to 9 theta nodes, which is 72 GPUs in total, we see almost a 2x runtime. This is strong scaling again, by the way. And similarly for RSBench large, we go to 9 nodes and we get only a 4x increase in runtime, as opposed to the one without the optimization, which reached over 16. So the kind of biggest advantages of this approach that we were trying to achieve and that we did was that we get reasonably efficient and highly scalable remote device offloading on commodity hardware as well as HPC hardware. It obviously can be improved by better usage of gRPC for commodity as well as Ucx for HPC. And we really hit the goal hard in terms of not requiring any source modifications when you're scaling. And because it's built off of LLVM and it already supports many architectures, we were able to sort of extend this very quickly. And we also know that you can also offload across architectures. So let's say you have an x86 host and an ARM DPU, you can offload in between them pretty easily. The sort of longer term vision that we have for this is that we want to obviously incorporate more UCX features. Right now, there are overheads that we get from tag matching that obviously we want to get rid of. Another avenue that we want to explore is compression, because the only time that matters here is the data transfer. So the less data we can move, the better. The sort of biggest thing is that we do want to find a way to get hierarchical offloading within OpenMP. It's not strictly supported by the standard yet, but we're hoping that if we move this work further along, we can get more support for trying to incorporate this into standard and have optimizations like the one we discovered for RSBench and NexusBench be sort of generically available to all of the programmers for all the applications. And sort of the biggest thing that we want is that we want to find more applications for this kind of easy offloading within SmartNICs and beyond that. So we can find more applications for this and see exactly the extent to which this is useful. And once again, I just want to reiterate, because this seems to get lost a bit at times, it's that we're not trying to come up with a competitor to any existing distributed programming model. We just wanted a way to allow programmers to use only remote GPUs, only remote CPUs, depending on whatever architecture they have, easily and without source modifications. Anyways, thank you for coming to my talk, and I'll open it up for Q&A, I guess.
Thank you for the nice talk. Are there any questions?
I have a question.
Sure.
And apologies for ignorance, probably I'm not familiar with OpenMP offload directives for GPUs. How do you deal with missing pages when you're trying to then compute run somewhere else and so on? Do you have like page fault handler?
So OpenMP, when you're target offloading with it, the expectation is that at the beginning of the region you sort of specify which arrays you're mapping to the device, and there are explicit copy operations that take it from the host to the device and back. So we don't have to deal with any sort of page faults, like at all.
Yeah, so it's kind of like a shadowing mechanism, basically.
Okay, no, I got it. It's sort of explicit, right?
Yes.
You have some declarations that will cause movement of the structure.
Absolutely.
And the assumption that you have symmetric OpenMP runtime everywhere in the system, I guess.
Yes.
Yep.
Yes. Although Although now the standard is supporting a unified shared memory, but in this case, I think that that we have that explicit copy in and copy out regions that we offload. Yeah.
And it's a SPMD programming model, right? As well, you assume that the same code runs everywhere.
I believe you can also do it generically, but typically SPMD tends to be much more faster and recommended. Yes.
Okay. Cool. Thank you.
And also, although OpenMP does have unified shared memory for I think a while now, we chose to not implement that as a part of this implementation because we felt that it kind of breaks the sort of abstraction that we wanted to provide in terms of having remote GPUs be exactly like local ones, and it'd be a lot of unnecessary implementation overhead, and we didn't really quite see the major wins that we could provide with it.
Yes. Yeah, that will require some sort of a layer for software DSM for creating sort of a shared memory across all the nodes. And
yep.
That's a
it is quite challenging to create unified memory across machines.
Yes. From the
it
days,
can go all the way back to Mosix, right?
Yes. From the days of Brett Marks from Rice University, they discover those sort of challenges. Page migration becomes a problem. Yes. One key question you mentioned about hierarchical target regions, which is a very interesting concept from the point of view of basically distributing the work, but also scheduling work that takes into account locality. Like, for example, thinking of an entire system as just an example, abstracting the entire system with a topology, right? Basically with let's like a tree topology or something along those lines, and being able to schedule those, those target regions to nodes in those trees, and to leveraging also potentially, take advantage of locality and things like that. So currently, I see that the problem that we see right now is that, one of the ideas is that you want to create those hierarchical abstractions, but currently, the other thing we need to think about, or at least figure out, is the idea of the data, right? Basically, distributing data, or figure out if that's needed, basically, because as you mentioned at the beginning, that you need to make copies of the entire data in all of the GPUs. So what are your thoughts in these two areas, basically the hierarchical offloading, and have you thought about data distribution, distributing data across nodes?
So particularly about hierarchical offloading, the sort of conceptual limitation that we have, it's that because OpenMP considers all devices to be equally spaced from it, there's no concept of accurately tracking locality from the program's perspective. So I guess the sort of simplest hack around this could be that within Clang, we just add a new clause that, hey, you can now group devices into nodes, and you can specify exactly by node. And then when you copy things, you can copy to nodes instead of devices in particular. And we could sort of all handle that within the plugin itself. But Johannes and I felt that would be much better served if there was a much more well thought out way of approaching it. So that's why we're kind of waiting on trying to get a better hierarchical model in place. And that in some way deals with the data distribution, is like I said before, that unfortunately OpenMP target offloading does require explicit memory management in terms of moving data back and forth. So we do need it to be that way. Additionally, something that we haven't really explored yet, but I'm really interested in trying to find out how to do this, is that is because we can offload sort of arbitrary OpenMP programs, and they don't even have to necessarily be parallel, right? It would be very interesting to see if we can offload from, let's say, one host onto a DPU, and have the DPU sort of, get data from the network chips and process it there before sending it to the host. And I think sort of non-accelerator based offloading could also be really interesting here. So we can sort of avoid the bottleneck, because one of the bottlenecks we have right now, right, is that even in the benchmarks that I've already run, that if you're offloading onto 120 GPUs from a single host, that's not a very fun way to do things. Ideally, you want to distribute that work along to more CPUs, and we know that there's no conceptual limitations. We just don't have any applications that aren't sort of toy ones to try to do this with. And every toy one that we try to come up with, it just felt a little flimsy, and we haven't found the right candidate yet.
Excellent. From one more question I have is, from the Ucx perspective, your experience of using Ucx basically to handle remote offloading, is there any feedback that basically you got from your experience that you might want to share with the community on features or things that you found useful or hard or to use, or things that you?
Not in particular with the API or anything, because so far I'm only using tag matching, so the API is pretty natural and standard. I did feel a bit, however, that just sort of in general, like I'm not affiliated with any particularly strong groups that have a lot of networking background. Like I work in the compilers team, trying to get more familiar with the sort of more interesting and sort of performance heavy features such as using RDMA, that I found to be a bit sparse in the documentation. But other than that, I don't really have any complaints about the usability or the quality of the interface provided.
Excellent. Did you? So this is also interesting because the work that you are doing here is somewhat has a lot of synergies with the previous talk on iFunk. Basically, and it would be interesting to figure out basically, if your implementation of UCX, if there is anything there that can be leveraged from iFunk or something along those lines. If there is anything in there that, what sort of things can be learned from each other either way. Just because I see some certain, a similar goal in the of programming remote devices or DPUs, and coming up with APIs to do that.
Right. So absolutely. Based on Wenbin's talk, I have to agree that the goals are very similar. It just happens to be at different levels of abstraction. We chose out of somewhat like what our background was, as well as some notion of simplicity to work off of the OpenMP one, because it already had a pretty well-defined API. Yeah, like there's definitely some UCX related knowledge or feedback or just experiments that I'm sure the people at iFunk have done could be really useful to us. But I think like there's a very sparse amount that I think we can provide back in the sense of performance knowledge or anything, because what we did was quite straightforward.
Yes.
At least so far.
Yes, that sounds very good. And what I find it also very interesting is that the model, you can express dependencies basically, and that's a very interesting feature for the model.
Yeah, so that's kind of why we decided to stick with using OpenMP, is because already it provides so many nice features for programming multiple devices, so including tasking, right, which has been a major thing for the past however many years. So it'd be great to sort of see how these tasks can be scheduled across many nodes, assuming that we actually get a usable form of hierarchical offloading.
Excellent. Yes. So I recommend to stick for the next two talks, because I feel like we're going to see interesting use cases that potentially could use some of these abstractions. At least I know for the last one, it would be interesting to try out. And but anyways, so
absolutely.
First of all, thank you very much, Atom, for your talk. I really appreciate it. And
thank you for having me.
Yeah, and looking forward to learn more as you progress with your implementation, and you are more than welcome to get involved in the UCF community.